Hey, I'm Joseph Huber. I work at AMD, and I'm going to talk about the project I've been working on recently, which is the LLVM C library for GPUs. So what is this thing? It's pretty much exactly what it says in the title. It's a build of the LLVM C library that's targeting GPUs. There's some documentation online that goes in a bit more depth, but I probably need to add some more. And suffice to say, all you should really need to do to use this thing is to set this fancy CMake variable like libc GPU build equals on, and that should give you this thing if you enable libc as your runtime. And it supports both AMD and NVIDIA GPUs. I went out of my way to make it work on NVIDIA because it's out of the goodness of my heart, so you're welcome. So, upon reading that title, many people's first question is, why would you want to do this? Well, initially I just wanted a portable implementation of printf for the GPU that existed in community LLVM, but after some interesting conversations with the libc team at the last developers conference, I figured I might as well just do everything else while I was at it. But it's more than just satisfying my morbid curiosity. It also allows us to port CPU applications and test to the GPU pretty trivially. It gives us some portable GPU math functions that are hopefully have more coverage than what's in like libclc upstream. And it also provides the basis for a lot more libraries, most specifically libc++, which is something people care about having on the GPU, I hear. So before I get too bogged down to the details, I just want to do a really high-level overview of what's really working right now. So if you enable it as was shown in the documentation earlier, you will get this static library, libc GPU, and libm GPU. And this is compatible with OpenMP, C++, CUDA, and HIP. Those last three have asterisks because it is not automatic. You need to do some manual user stuff that I don't describe here for brevity's sake. But it supports a lot of the common libc functions already that you can think of. On the right here is a screenshot of what the documentation page says. I'm adding more stuff as I go. But what does this thing even look like to use? Well, on the left you have some standard OpenMP offloading code, which calls the fprintf function with 4 threads on the GPU. So you can see we compile it, tell it to use OpenMP with offloading to whatever GPU we have, and we link in the cGPU static library, which will bring in the GPU state runtime. So that'll link into fprintf, and when you run it, hey, we printed from 4 threads. Now you might also think, hey, what if we just don't use any offloading language at all and pretend like the GPU is just a standard cross-compiling target like ARM or RISC-V or whatever? Well, you can do that too with the same infrastructure. You can just compile to C++ and use the cross-compiling -- targets at your CPU, and use the C library we made and the startup code to call the main function, and then use this loader to basically just tell it to launch this GPU executable we just made, and hey, we can print from 4 extra threads, and we successfully tricked people into thinking that the GPU is a normal target. So that support allows us to run 3 extra build bots, which are currently executing about 125 something tests from the LLVM libc test suite. And we have 1 on the AMD architecture and 2 on the NVIDIA architecture, thanks to JP from AMD and Artem from Google for setting those up for me. Alright, so that's the really high-level stuff. Now I'll talk about some of the details. Well, the LLVM C library is written entirely in freestanding C++, so that's what encouraged me to kind of ignore a lot of the traditional stuff about offloading languages, because I wanted to be single source with this stuff. I didn't want to have too many things that diverged from what's upstream with the other CPU targets. And what's really brought me to this project was that it was designed from the start to be, easily decomposed and ported, and I was like, hey, let's see how true that really is and put it on the GPU. But to that end, it allows you to make custom system headers that we can use to actually put things on the GPU. You can define which functions you actually want to support, which is really good for incremental bring up of certain functions. And you can also even decide what the standard function specification you're targeting is. And that's actually useful for extensions if you want to do GPU specific stuff. It's not really libc stuff. Okay, so as mentioned before, this is just C++, so why don't we just target it with cross-compiling? On the left, I just have a thing I copy-pasted from the libc source upstream, which implements the string compare function. And you can just take the same C++ code that you would compile for like x86 or ARM or whatever, and compile it targeting the GPU as with like 2 flags I've shown here, for example. And any architecture specific stuff you're doing, you can already handle it. Like people are used to handling this stuff with if-defs and built-ins, so it's kind of the same magic you'd do if you're on any other target that has really specific stuff you need to target. And once you build those IR files, you can pretty much just bundle them in a static library so you can link them with whatever your language of choice is. And this is a slide I just included that is a screenshot from the Compiler Explorer. And it's just to illustrate the fact that if you really want to see what something looks like on a GPU, you can just compile it targeting the GPU. You don't necessarily need to use like CUDA or OpenMP or whatever. You just want to see what the IR looks like. Okay. So now that we can like compile to C++, you should be able to just make a regular executable, right? So how do you want to execute that? Well, all we need to do is really just have some kernels that do things like call global constructors, destructors, and execute a main function. We can put that in a startup object, like what the regular libc does to call your main function. And the only difference here is that we need to have a GPU runtime executable that just launches those kernels. So once we do that, we can just compile something to a GPU executable, use this AMD HSA loader utility or NVPX loader utility, which is just a very minimal runtime for the respective GPU that will launch the kernels necessary to pretend like this is a standard target. So now that we have all that, we should be able to run anything on the GPU, right? Well, I'm sure many of you are familiar with the many functions that require things from the operating system to function, like exit or printf or malloc, things that a few people might care about. The GPU doesn't really have an operating system we can use, but it does have a host that's executing, and that has an operating system. So what we can do is implement remote procedure calls to basically tell the host operating system to do something for us and then give it back. So that's exactly what we did. So I'll try to do a really high level overview of what this looks like in practice, but pretty much all GPUs these days support some form of device accessible host memory. So this is the type of stuff you get from hip host malloc or CUDA malloc host. Suffice to say that this is memory that both the GPU and the CPU can access asynchronously while both are executing. And since a while back, this type of memory has also supported many atomic operations. So if you have some shared memory and atomic operations, then you can do mutual exclusion on a shared buffer, which means you can just swap things back and forth between a client, which would be the GPU, and a server, which would be the CPU in this case. So pretty much, if you have these mailboxes, it pretty much says, hey, I want to give you ownership of the buffer, and then the other side can say, hey, I want to give you ownership of the buffer. So given that, we can just atomically wait until we own the buffer, use the buffer, and then give the thing back to the other side. And that's pretty much all you need conceptually to say, I want the server to do something. I just give it some value, and then it waits until it has it, and then it gives me the result back. It's pretty simple. So if you take the same buffer and then just add an opcode on top of it, you're pretty close to what a syscall is. You know, it's just an opcode that does a thing, and then a bunch of data that you want to do with, do the operation on. Obviously, GPUs are not well known for their single-threaded performance, so we can't just have this one-to-one server-client model. We need to scale this up to multiple threads, and the way we do this is by abstracting ownership of this shared buffer into a port, and then ownership of that port is then restricted by a lock. So you just get mutual access to the shared memory on both sides using this lock. And this pretty much gives you a thread-safe, many-to-many protocol that you can use to just swap data back and forth. It's all pre-allocated, so you should know exactly what you need when you need to use it. And that's not exactly the end story for the GPU, because GPUs are actually a little weird. So, as many of you know, the smallest unit of actual parallelism on a GPU is not a thread like they tell you. They actually lie to you. It's a warp or a wavefront, which is like a group of 32 or 64, maybe 16, I don't know, threads. So suffice to say that we need to essentially have the granularity on this operation to take a whole warp or wavefront in account when we execute this. And pretty much all that means is we just need enough buffer space to store all of the threads inside of the warp, and then a mask for which ones we actually care about. So, and then once you have that, you pretty much just put a bunch of these next to each other, and then you have some highly concurrent thing that a bunch of threads from the GPU can push work onto and wait until the host figures out what to do with it. So given that super high level description, we can abstract that into what is actually the API that I use internally in the libc, which is kind of more of a send and receive type thing with a fixed size packet. So you can see on the right, we want to, let's say, increment this value on the CPU for whatever reason. We tell the RPC client to open a port with this RPC inc opcode. Then we get our port and then use it to send data by writing our count to the buffer. We will then, on the server, detect that we own that port so we can open it and then check what the opcode is. We see that it's this RPC inc, so we know what to do with it. We read the first thing out of the buffer, increment it, and then send it back. And then the GPU will receive that back, close the port, and it will continue on with its merry way, having successfully offloaded some work to the CPU. And this pretty much gives you an extremely flexible way to do pretty much anything you'd want to do on the host from the GPU. You could even use this to call function pointers or anything, pass it some struct as if this was pthreads, that type of stuff. And that's exactly what I did for this graph, because upon telling people about this weird RPC stuff, the first question they might have is, how slow is this? And it turns out that calling a function pointer from the GPU via RPC is roughly equivalent to the latency of an actual kernel call from the CPU, which shouldn't be too surprising because it's like going over the same TCI bus. But basically you can think of these as like reverse kernel calls in terms of performance. So now that we've got all of that working, we can successfully take the LLVM C library and compile it entirely for the GPU. So the LLVM C library test suite is pretty much a gtest-like suite. You can see an example on the left for that string compare. And it's got a bunch of like global constructors and destructors in C++ that runs and executes your function and checks what's right. But the interesting thing about it is the C library, the LLVM libc, has their test suite that is completely self-hosted. So it doesn't require the can execute it with purely things that are built in the repository. And that's really useful for putting it on the GPU, because then we can just compile all of that stuff that's in libc for the GPU, use the infrastructure I just talked about, and now we can just compile a test on the GPU. So we take all these tests, run them on the GPU as if we were cross-compiling, and as I mentioned before, we've got about 125 extra GPU tests that are running on the build bot, so that's good. It's always, and especially these tests are interesting because a lot of the times the types of tests people write for the GPU backends are very close to what they expect the GPU to actually do. So I consider this a form of fuzzing by forcing it to do this weird stuff. Okay, so, and this other thing, I'm actually looking into if there's a way to get the LLVM test suite, like the other one, to execute in the same way using, similar infrastructure. I think there's a work by Chile that was doing that. So we could put that on a build bot. All right, so that's pretty much the very high level overview of what this is. And before I close out, I'll just go over a few pain points that have various solutions to, and maybe none. So currently we can't really support thread local, which makes implementing things like errorno or rand a little difficult. I don't know if people really care about errorno on the GPU, but they care about it a little, not much on the CPU, but who knows. Rand is a bit more, maybe you'd want that. But there are ways we could probably implement this. We have some ideas, but it requires time that people haven't invested yet. Another problem is linking the libc with LTO is problematic, because the reason I can do this as a static library without worrying about massive, function call overhead, which I've heard people who program on GPUs care about, is because we can use LTO. But one problem is that the LLVM libc is compiled with freestanding, and there's some logic in LLVM that basically says if you are compiled with freestanding, you cannot be inlined into code that was not compiled with freestanding. So pretty much it prevents us from inlining any of these functions currently unless you pass -fno built-in. I'm looking into how to fix that. Supposedly it was related to like a bug of infinitely inlining implementations of memcopy. That's all I know. Okay, another problem is that we currently can't build the CPU and the GPU libc at the same time, but I heard that there was a talk earlier today where they were talking about bootstrapping the LLVM libc onto the LLVM libc++, which would give us a third level of bootstrapping, which we could then make these separate CMake invocations, and that would go away because then you could just bootstrap the CPU version and then use that to build the GPU version. So maybe we'll figure something out there. And I'm not just saying this because I work at AMD. The NVIDIA toolchain has some things that make this a little difficult. For example, NVLink, which is their linker, does not support static libraries. So you can't really do the same level of fancy stuff like I did in the first introductory slide, because you only have object files. You need to pass every single object file on the command line. And also, they don't have the section keyword in PTX, so if you ever want to put things in a section, you can't do that. And finally, multi-architecture support. It should be a single bitcode file, but right now I do the really easy solution and just compile it for every single GPU architecture I expect to be run on this thing. I'll fix that eventually. Alright, so in conclusion, I built the LLVM C library targeting the GPU, and it turns out that compiling freestanding C++ for the GPU works surprisingly well. And, it's not super surprising when you think that, most offloading languages are pretty much just C++ with some built-ins made to look like nice little keywords. So, created this libc GPU and libm GPU, which are just static libraries that you can link. They're fully integrated into OpenMP offloading at the moment. So if you build this libc thing and use OpenMP offloading, you should just be able to call all the supported libc functions that are mentioned on the webpage. And like I said, this works with CUDA and HIP, but it's opt-in, and you need to manually write the RPC server part. So I've done it. I can confirm it works, but I don't think many people know how to turn it on yet, so I'm working on that. And another interesting thing is the RPC infrastructure, which pretty much you can reuse to do most any host services you might want. It's very extensible, so I'm hoping that it provides the basis for other complicated things people might want to do on the GPU to the CPU. And we have a lot of stuff upstream. This is all upstream. You can use it now. As far as I'm aware, if there's bugs, just email me angry messages and I'll get around to fixing it. And there's build bots. That's always good, I've heard. And hey, looks pretty well. Okay, so before I close this out, I just want to thank John Chesterfield from AMD, Johannes, Brian Sumner, Tian, Siva, Tu, and Michael. So thank you. That's all, so any questions?
Questions?
Hey, nice talk. You talked about the CUDA host, malloc host, and then creating all of these gRPC servers between the CPUs and GPUs. Did you try the CUDA malloc managed, which is the same buffer that's getting shared between the CPU and GPU, specifically for NVIDIA? And what was your experience with it?
Yeah, I think the malloc host and the malloc managed, I forget what the specific difference is.
Unified memory.
Yeah, so unified memory is a different.
Unified.
Yeah, it's slightly different because we can't always expect it because it's only in the super new systems. There's a lot of things that unified memory simplify, especially in the RPC interface. For example, if I want to print a string, right now, if it's not unified memory, I need to copy the whole string. If it is unified memory, I can just give you a pointer. But I haven't really done anything specifically with unified memory in this context because you kind of need to make it work on most systems, and then you can start specializing to the really fancy ones that have unified memory and are on the Linux systems that actually support HFM and stuff. So,
another follow-up question was, you talked about SM75, which is an older NVIDIA. Mm-hmm. Anything to do with the SM80 or the later versions of NVIDIA? Okay, so at home I have a server with an SM89, Ada on it, and that's my development machine, and it runs just fine. So it's SM89 with the RTX stuff. So that's the newest one I've run it on.
So you had this one slide about performance where you talked about, multi-threaded. But what about, like, this is like a no-op. This is just overhead, right?
Mm-hmm. Yeah.
But what about other types of performance studies? Do you have any numbers, things that, like, parallelism? I mean, GPUs are good at parallelism. What happens if you hit this hard?
So AMD discourages very hard performance numbers from being published in public talks. So this is why I did the relative measure. I have done bandwidth tests for how much you can actually print from the GPU. It's like somewhere between 10 to 100 times slower than doing it on the CPU, which isn't that bad, all things considered, It's within the fact that it's within, many megabytes per second, Most people probably aren't going to worry about more than 100 megabytes per second bandwidth when doing printf from the GPU. That's just what I'm going to say. But yeah, I haven't done anything super specific performance-wise, mostly because, one, I'm still developing this, and two, I wouldn't be able to put it on the slide.
Okay, thank you.
So, I mean, do you support target x86 64 or assume I don't have a GPU, so I want to test my RPC calls and everything, right? Go to the full infrastructure.
Okay, I have done that before, but it's not like actively tested. So when I was developing this thing, it was CPU to CPU because CPUs are really nice because they have debuggers and stuff. So when I was initially writing this stuff, it was a lot of some x86 thing communicating to another x86 thing. So it works, but I'm not actively testing it. So thank you.
So you don't have plans of pushing it up, right?
Well, you could definitely use it because it's a header-only implementation. The only reason we don't expose the header is because it's kind of internal to libc, and we don't want to leak too many internals there, but I could definitely just copy it somewhere else, and then you could just include rpc.h and use that on anything that has realistically, the only limitation here for this framework I made is whether or not it has a shared memory buffer that can be atomically accessed with, I think the only thing you need is like test and set or something.
And your utility will still support the same thing, right? Mm-hmm. Offloading, okay.
Yeah.
So can this library be used from both host and device code?
Repeat, please.
So you showed that this was ported to GPU, which is fine.
Yeah.
But in a CUDA code, there is some host code and there's some device code.
Okay, so this is, I actually forgot to mention it when I did the thing. Okay, so this thing that I totally forgot to mention, the libc headers and host headers need to match and cooperate. So CUDA specifically has, at least on CUDA Clang, which is what I'm targeting, has specific device and host side overloading. So we can provide different implementations for the host and the device. The way I export this is with a bunch of declarations for what my libc provides to the GPU. And when you're compiling for CUDA, the header basically says device, device, device. So when you're executing in a kernel or in a device region, it'll use the device version. Otherwise, it'll use the regular system version. Thank you.
Do you know how difficult it would be to replicate it for libc++?
No, I'm assuming very, but I'm going to work on it, okay? I'll probably start hounding the libc++ people eventually. So be prepared if you're in here.
Okay, any last questions?
So is it enough to have just atomics there, or do you need to have any fencing?
Well, you definitely need fencing, but that kind of comes with the... so you need a lot of fencing to make sure that you don't give ownership away after my wait for the ownership, because that would be totally broken. So you definitely need store and release fences around that. The atomics are also difficult because I didn't really mention it specifically, but we use, if you notice, we use like two mailboxes, and the reason is because you can't just use toggle XOR, and that's because potential implementations of the atomics on this shared memory could be through PCI atomics, which don't have XOR, so we kind of needed to use a really limited set, which is pretty much just stuff like test, set, and fence. So that's, if you have a really minimal set of atomics, you can't use this thing, but you kind of want to, we intentionally restricted it to those because the implementations of atomics are kind of sparse in this area.
Thanks.
Thank you.
All right. Thank you so much, Joseph. Great talk.